Here is a plot showing the infection rate of the Code Red 1 version 2 worm, which ultimately infected 350,000 vulnerable hosts. Note the shape of this curve. The worm is effectively dormant or spreading extremely slowly for quite a period of time, and then there's an inflection point, at which point the infection rate becomes exponential. At some point then, infections slow, and the infection rate ultimately plateaus, presumably after all of the infected hosts have been found. We can actually model the spread of these worms using the random constant spread model. If k is the initial compromised rate, n is the number of vulnerable hosts, and a is the fraction of hosts already compromised, we can now express the number of hosts infected at a particular time increment in terms of the machines already infected and the rate at which uninfected machines become compromised. So if NDA is the number of newly infected machines in DT, we can express that in terms of the number of machines already infected, which is N times A. So these are the hosts already capable of doing more scanning. And now K times 1 minus A is the rate at which uninfected machines become compromised in a particular time interval, dt. If we solve for A, the fraction of hosts compromised, which is effectively the y-axis of this graph, then we get the following. You get an exponential curve that is exponential where the growth rate depends only on K, or the initial compromise rate. This is very interesting because it tells us that if we want to design a very fast-spreading worm, then we should design a worm such that the initial compromise rate is as high as possible. So how do we increase K? Or how do we increase that initial compromise rate?